Hello and welcome to all my young friends who are studying in intermediate and they are watching this video. Welcome to Calculus Made Easy series. Till now in calculus we have discussed limits and then we discussed continuity. As we indicated earlier, after that comes the topic of differentiability. But before understanding differentiability, we have to understand what is a derivative. And then we'll talk about differentiability and then the process of finding derivative, which is called differentiation. So let's understand derivative, the concept of derivative. What is derivative? Derivatives is rate of change of a function. Suppose y is equal to fx is a function. Derivative is represented by dy by dx, means change in y with respect to change in x. Then we talked about differentiation. What is differentiation? The process of finding derivative. We also call it differential coefficient, or differential coefficient is called differentiation, which we'll discuss after differentiability. Now let me give you one example. Suppose you plot speed versus time for a moving body and you get a graph like this. That means at t1 time its speed was s1 and at t2 time the speed became s2. Now what is rate of change? The speed became s2 from s1. That means s2 minus s1 is the change in speed. In how much time? t2 minus t1. So this is rate of change of speed with time. So we'll write like this. Now if this is A, B and C, now s2 minus s1 upon t2 minus t1 is equal to BC upon AB. And suppose this angle is theta, BC upon AB is equal to tan theta. That means rate of change in this case is tan of this angle. So tan theta represents rate of change of this function, which is represented by a straight line. Now just see one more peculiarity of this function. You take any time interval, say this is a time interval t, and in this time interval the change in speed is say s. So if you complete this triangle, if this angle is theta, this will also be theta. So here the change in speed is s and time is t. So s upon t again is tan theta. That means you take any interval, the rate of change is always same because it's a straight line. You can take interval anywhere. Say you take an interval here, t dash and speed change s dash. Again, this angle is theta. So s dash minus t dash is again tan theta. So similarly, you can take interval of time anywhere in this figure, and you will find that the rate of change is constant because slope of this line is constant. It's a straight line. Now, but if you have a graph like this, here also the speed from s1 it becomes s2 in time t2 minus t1, but variation is totally different which is represented by this zigzag curve. Now, how do we find rate of change for this function? If you say S2 minus S1 upon T2 minus T1, fine. In T2 minus T1, it has changed by S2 minus S1, but this is an average rate of change. But if you look at the figure, here the speed is increasing, here it is decreasing, here again it is increasing, decreasing, again increasing, decreasing, and increasing. So how do we find rate of change at any point? In our previous example, you take rate of change in any part of the curve, that was same, but here it's totally different. So now we'll talk about the concept of dy by dx. Say if you have a curve like this, y is equal to fx, here also it's not a straight line, it's a curve. But I have made it a smooth curve so that it is easy for you to understand. An unnecessary zigzag curve will be complicated, but more or less, you know, it's going to be same whether you take any kind of curve. You take 2 points on this curve, A and B, which are very close. Only I have depicted just to show you. Say the coordinates of A are x and y, that is, this is x and this one is y. Now B is slightly ahead of A, very close to A. See, if you just make some change in A, say, x plus delta x. So that means if you make delta x change in x and then you draw perpendicular, it will cut the curve at B. So now since this is delta x, the change in y will be small change delta y. If you make a small change in x, it will be a small change in y. It can be positive, it can be negative also. Suppose the curve is like this. So delta y will be negative. That doesn't matter. So here, with a small change of delta x, you get a small change of delta y. Only thing is, I'm again telling you that I have made it big so that it is easy for you to understand. Now join AB. Suppose this is theta. What is delta y upon delta x? This side is delta y and this side is delta x. So delta y upon delta x is equal to tan theta. That means it is slope of this line AB, right? Slope of a red line AB. Now we slowly bring B closer to A. Say B is at this place. On this curve itself, we bring slowly B closer to it, like this. What will happen? A bit more closer. Now you can see this slope of this line is changing, right? Bit more close, even more close. Now, as delta x tends to 0, B tends to coincide with A. And then this straight line, red line, becomes tangent at A. When delta x tends to 0, just see again, when this delta x tends to 0, when you make it nearly 0, then B tends to coincide with A. And this line becomes tangent. Red line becomes tangent at point A. Now the slope of tangent delta y by delta x when delta x tends to 0 is called dy by dx. That means, hence, limit delta x tending to 0, delta y by delta x, this is called dy by dx. Right? What is dy by dx? Is equal to limit delta x tending to 0, delta y by delta x. We'll again repeat it. Join AB. This angle is theta. Delta y by delta x is tan theta. Bring B closer to A, being on curve. When B just coincides with A, this red line becomes tangent. And delta y by delta x is the slope of the tangent. When this line becomes tangent at A, then delta y by delta x, limit delta x tending to 0, is called delta y by dy by dx. dy by dx is called derivative or differential coefficient. So, what we discuss, dy by dx at any point, please note, at any point is equal to slope of the tangent at that point. Is equal to slope of the tangent at that point. And dy by dx is equal to limit delta x tending to 0, delta y by delta x. Suppose you have a curve like this and you require to find dy by dx at different points, say A, B, C, D, E. Now what do? You just draw a tangent at A. If you want to find the rate of change at point A, you draw a tangent. You want to find at B, again draw a tangent. At C, draw a tangent. At D, draw a tangent. At E, draw a tangent. Now you measure their slopes. If this angle is theta A, then dy by dx at A is tan of theta A. Now this angle is acute, so this is positive. Tan of acute is positive. This is theta B. dy by dx at B is equal to tan theta B is less than 0 because for obtuse angle tan is negative. Say this is theta C. dy by dx at C is tan theta C. Again it is positive. This is obtuse theta D. dy by dx at D is tan theta D. Again negative. Theta E. dy by dx at E is tan theta E. Again positive. So here it is positive, so function is increasing. Here it is negative, say function is decreasing. Here again it is positive at C, function is increasing. Here it is negative, function is decreasing. Here again it is positive, function is increasing. So if the function is increasing, dy by dx will be positive. If function is decreasing, dy by dx will be negative. I hope you are clear with this. Now, how to find dy by dx, that is derivative or differential coefficient? of a function, say y is equal to fx. Now we already know dy by dx as per definition is equal to limit delta x tending to 0 delta y upon delta x. So you have y is equal to fx. That means a small change in x will bring a small change in y. That means y plus delta y is equal to f x plus delta x. It may be positive, negative. If you increase x, delta y will be negative also. It depends upon the nature of your curve. But x plus delta x means a small change in delta x will bring a small change in y. Now, delta y is equal to, from this, f x plus delta x minus y, and y is equal to fx. So this is f x plus delta x minus fx. So delta y upon delta x is equal to f x plus delta x minus fx upon delta x. dy by dx is equal to limit delta x tending to 0 delta y upon delta x, which is equal to limit delta x tending to 0 f x plus delta x minus fx upon delta x. So this is the, you can say, formula and steps to calculate dy by dx, which we'll be using shortly to calculate derivatives of standard functions. We can have any type of function. Say, let me give you one or two examples. Say y is equal to fx, say is equal to sine x. So y plus delta y is equal to f x plus delta x, which is equal to sine x plus delta x. So dy by dx is equal to limit delta x tending to 0 f x plus delta x minus fx upon delta x, which in this case is limit delta x tending to 0 sine x plus delta x minus sine x upon delta x. This is your dy by dx in this case. So you'll say how to, calculate this or solve this. This we'll be discussing later. Let me give you one more example. Say we have y is equal to x raised to the power n. So y plus delta y is equal to, you can write fx f x plus delta x plus delta x whole raised to the power n. So dy by dx is equal to limit delta x tending to 0 f x plus delta x minus fx upon delta x, which is equal to limit delta x tending to 0 x plus delta x whole raised to the power n minus x raised to the power n upon delta x. So this is how you calculate the derivative of any function. A very basic uh, examples I have given. We will be discussing this in detail when we find derivative of some standard functions, which we'll be doing when we cover the topic of differentiation. Now, it may not be possible for us to find derivative for a function at each and every point. Maybe the function may be differentiable, the function may not be differentiable. So today our topic is differentiability. Here we'll check what are the cases when function is differentiable. That means its differential coefficient or derivative, whatever you call, can be found. So let's start our topic. So derivative for a function exists or function is differentiable. They are the same thing. Two ways of saying the same thing. If and only if. This symbol means if and only if. Left hand derivative and right hand derivative exists and are equal. That means derivative for a function at a point exists if left hand derivative and right hand derivative exist first of all. This is your first condition. They should exist. Then they should be equal. Then only the function is differentiable. But now you may ask what is right hand and what is left hand derivative. So what are left hand and right hand derivatives? So let me explain you what are left hand and right hand derivatives. If this is y is equal to fx, we take a point on the function. The coordinates of a are xy. This is x and this is y. Similar to what we did in our previous video for finding dy by dx, we move a bit ahead in x-axis direction, that is delta x, and reach a point b. This is delta x. Although I have shown b to be at a distance, but it is quite close. This is just to show you. Delta x is very small, quite small. Now, what we do with small change in delta x, there is a change in y, which is delta y. We just join AB. Now, delta y upon delta x is slope of AB. Now, dy by dx is defined as limit delta x tending to 0 delta y upon delta x. That means the slope when del of AB when delta x tends to 0, it nearly becomes 0. At that time, whatever the slope of this line, that is equal to dy by dx or the derivative, whatever you. That means delta x tends to 0 means we are bringing b close to a. That is what we discussed in our last video, concept of derivative. We slowly bring b closer to a. Now, slowly we bring it closer to a. Now, when b just coincides with a and delta x tends to 0, at that time, limit delta x tends to 0, delta y upon delta x is slope of this red line. This slope is called the right derivative. Why we call it right derivative? Because we went on the right side of A, we took B on the right side of A, and then we move B closer to A. Similarly, if we take B on the left side, like this, so this is delta x, this is delta y, we join AB, and again we move B closer to